All right, so what we're going to talk about today is dividing polynomials, which is going to be crucial because to find zeros of polynomial functions, we need to know how to divide to be able to see if a certain zero of a polynomial exists. So we're going to start off. So our main goal in the beginning is going to be to divide polynomials using two methods. Okay, so the first method is kind of what you saw in elementary school, which is using the idea of long division. Okay, and so what I want to comment here is that using long division to divide polynomials is identical to the method we learned in dividing numbers using long division. In fact, the only difference is, so we would say that the only difference is we only use, or we use the leading terms to decide what to multiply. So just to kind of point this out, like if you remember in elementary school at some point you said, hey, how do I use long division to divide 3 divided by 5? We would basically say, well, this was 3, this is 5, and then you'd say, okay, 5 is bigger than 3. So you'd add a decimal and make this 30, and then you say 5 times what is 30 and get 6. This is 30. You subtract, you get 0 as your remainder, so it's 0.6. So we're going to use the same idea as this to divide 3 by 5, except now we're going to see polynomials. So let's look at an example where we'll put this to use. So for A, we're going to say divide 8x cubed minus 3x squared plus 2x minus 1 by x plus 2. Okay, so when we do this, we basically say, okay, well, I'm going to use long division for this. So we're going to say the x squared minus 2x plus 2 is what we're dividing by. So this will be 6x to the 4th plus 2x cubed minus x plus 2. Okay? So with that said, now what we're going to do is we're going to basically take the leading terms and say, okay, what do I need to multiply to this x squared to get 6x to the 4th? We're going to need to multiply by 6x squared. So then, this is wrong. This should be x plus 2. I was looking at your next example. So this is by x plus 2, so this should be x plus 2. So we're going to say the same thing. What do I need to multiply to this x to get 6x to the 4th? It's 6x cubed. So if I multiply that, I get 6x to the 4th, and then 6x cubed times 2, that's going to give me plus 12x cubed, and then we subtract them. 6x to the 4th minus 6x to the 4th, gone. 2x cubed minus 12x cubed is minus 10x cubed. and then we carry everything down. And now I look at the leading terms again. What do I need to multiply to this x to get negative 10x cubed? I'm going to multiply negative 10x squared. So hopefully you're seeing this process is identical to just dividing numbers. So this will be negative 10x cubed minus 20x squared, and then we subtract them, and then obviously these will cancel out. This 20x squared, there's no x squared here, so this will just be, there's nothing else I could combine, so that will become just a positive 20x squared minus x plus 2. And then for this I'm going to multiply by what do I need to get 20x squared? Just by 20x. So this becomes 20x squared plus 40x, and then we subtract and we get negative 41x plus 2, and then lastly we multiply by negative 41, which gives us negative 41x minus 82, and then we subtract them and we get 84. So this was my remainder. So in other words, what we're saying is when we divide 8x cubed minus 3x squared plus 2x minus 1 by x divide x plus 2, we end up getting 6x cubed minus 10x squared plus 20x minus 41 plus 84 over x plus 2. And this is basically the remainder that we had. Okay, so for example 1 part B, why don't you guys pause the video, do this on your own, and then press play and see how it compares. So for C, we're dividing 6x to the fourth plus 2x cubed minus x plus 2 by x squared minus 2x plus 2. Okay, now one other comment that I want to make is this. We're going to put the x squared minus 2x plus 2, and here's something that I would recommend that you do, which I didn't do in part A, and then it's just to keep things clean. Notice how this was x to the fourth x cubed, and then it jumps from x cubed just to x. The whole idea becomes, well, since it jumps from x cubed to x and it doesn't have an x squared, why don't we just leave it as, or put it in place, plus 0x squared minus x plus 2. So why am I doing this? And this term hopefully looks similar to you because we use the same thing in part A, but now we're dividing it by something else, which not a big deal. But when you look at this, we skipped from x cubed to x, so notice how the x squared is zeroed out. So this will kind of help us just to keep things aligned, and you'll see what I mean. Compared to A, there's some minor difference that we saw. So what do I need to multiply to this x squared to get 6x to the fourth? I'll need to multiply 6x squared. All right, so that'll give me 6x to the fourth. That'll be minus 12x cubed plus 12x squared. So notice how this x squared lines up with that x squared, which is nice. So it's kind of like keeping all the same powers together by me putting that 0x squared. So you don't have to do it, I just think it just makes it cleaner. So 6x to the fourth minus 6x to the fourth gone. 2x cubed minus negative 12x cubed, which becomes 2x cubed plus 12x cubed, which is 14x cubed. 0x squared minus 12x squared is minus 12x squared minus x plus 2. So then we just carry everything down. So we do the same thing. So for this, I'm going to have to multiply 14x, which gives us 14x cubed minus 28x squared plus 28x. And then we subtract. So we get, that zeroes out. Negative 12 minus negative 28, which becomes negative 12x squared plus 28. X squared becomes 16x squared. Negative x minus 28x is minus 29x plus 2. Okay, and then this is going to be the last time we perform this, it looks like. So I would just need to multiply this by 16. So when I multiply by 16, I get 16x squared minus 32x plus 32. And then if I subtract them, This becomes negative 29x plus 32x, which is 3x. 2 minus 32 is negative 30. And that's my remainder because, look, this is 3x, that's x squared. So I can't go any further. So this just becomes 6x squared plus 14x plus 16 plus 3x minus 30 all over x squared minus 2x plus 2. Okay, so that's using long division. Now, the second approach is by using synthetic division. Okay, so synthetic division, and I'm sure you've seen it last year also, this only applies to divide by binomials. So if you think about it, in part B, since we're dividing this by a trinomial, I cannot use synthetic division on this. Okay, so I would have to use long division. But if it's a binomial, then I can. So we would say that this is a method that is used to divide a polynomial by a binomial of the form x minus c. Okay, so let me just kind of show you the process, and I'm sure you've seen this, and we'll do some examples. So to divide a polynomial, which a general polynomial looks like a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub 2x squared plus a sub 1x plus a sub 0 by x minus c using synthetic division, we will follow this process. So what happens is, since we're dividing by the x minus c, and remember, since it's minus c, just we make kind of like this box here, and then we're going to put the c here. So this c that we see there, we put there. So remember, if this ends up being like x plus c, then we put a negative c. So for example, if it's x plus 2, we put a negative 2. If it's x minus 2, then we put a 2. All right, so we want it of the form x minus c. So whatever c is, that goes there. And then what we do is we take the coefficients of our polynomial. So we'll put what? A sub n minus 1, all the way until we get to a sub 0. And remember, if let's say the x cubed is missing, then we put a 0 in for its coefficient. So we have to start from the highest degree and work our way down all the way to the constant. So if my polynomial function doesn't have an x cubed, it in fact does. The coefficient in front of the x cubed is 0. Okay, so just keep that in mind. So then what we do is, if you remember the process, we would bring this a sub n down. And then what would I do? I would take this, then we would multiply that to c. Okay, multiply to c. After you multiply to c, then what do I get here? I get basically a sub n times c, right? Because that's what I get, and I put it under the next term. And then what is it that we do here? Then we would take these terms and we would add them, and you get a sub n minus 1 plus a sub n c. And then what do? We follow this process again. Then we multiply again, and then we bring it to the next term. So we're kind of just repeating this process. So over here, I'm going to say repeat the process until all terms are multiplied. Okay, and then one thing I want to point out is you get a number here at the end when you repeat this process. This last number is the remainder. So it's like if you're to go through it, if this is 0, then that means our remainder is 0, which means it divides perfectly. If we get something other than 0, then we have a remainder. Okay? So then what you notice is by creating this process, on the bottom here, right here, we get a bunch of new numbers. And what this is, these new numbers become the coefficients of a new polynomial. And what's nice about this is the new polynomial we have is just 1 degree less than the original. How come? Because look, we're dividing by x minus c. And if I divide by x, what am I doing? I'm bringing the degrees of these guys down by 1. So what I would say is that this is a new polynomial with degree 1 less than the previous polynomial. Okay, and then these become the coefficients of your new polynomial. Okay, so with that said, let's look at our second example where we'll apply synthetic division, and then you'll see that this will kind of be in play, so it'll all work out nicely. Okay, so now for example 2, we're going to say use synthetic division to divide (5x cubed minus 2x squared plus x minus 10 by x minus 3. Okay, so then what is it that we're doing? We put the 3 here, and then notice how this is x cubed, x squared, x constant, so we're good. We don't have to worry about adding a 0. But if, like, let's say the x squared was missing, it was just 5x cubed plus x minus 10, we would put a 5, then a 0 because the x squared was missing, and then a 1 and negative 10. So remember, we need to make sure that we have a placeholder for every single one of these, starting with the highest degree, working our way down to the constant. So this one is just going to be negative 2, 1, negative 10. So now we just start the process. So this becomes, you bring the 5 down, 5 times 3 is 15, 15 minus 2 is 13, 13 times 3 is 39, 39 plus 1 is 40, 40 times 3 is 120, 120 minus 10 is 110. So this says two things. Number one, we can't cleanly divide 5x cubed minus 2x squared plus x minus 10 by x minus 3. And if we do, this is going to be our remainder. It's 110. So what would that be? My new polynomial would be this, right, which would be 1 degree less. So since that was x cubed, this one will start off with x squared. So that's my x squared, that's the x, that's the constant. So it'll be 5x squared plus 13x plus 40, and then we have a remainder, which is plus 110 over x minus 3. Okay, so there you have it. We just use synthetic division. Just remember, the only thing about synthetic division is you could only divide by binomials. Okay, so let's move on to our next theorem, which has to do with the remainder theorem. So the remainder theorem is a very nice and convenient way of checking to see if a polynomial is, or if a binomial is a factor of a polynomial. So we would say, look, if the polynomial p of x is divided by x minus c, then the remainder is the value p of c. So what is this saying? Like, hey, if you're dividing a polynomial by x minus c, to find out what your remainder is, all you have to do is plug in c in for x. Now, why is that convenient? Because see, our goal is going to be eventually to factor completely, cleanly, which we'll talk about later on today. Which, what does that mean? If I want to cleanly be able to factor out x minus c, that means when I divide this out, I want my remainder to be 0 always. Because when the remainder is not 0, then that means it doesn't cleanly factor out. But when the remainder is 0, then that means it does cleanly factor out. So let's look at our third example. So we're going to say let p of x equal to 8x to the 5th minus 2x to the 4th plus 10x cubed plus x squared minus 20x plus 1. Okay, so the question then becomes, for part A, find the quotient and the remainder when p of x is divided by x plus 2. Okay, so for this one, what we're saying is, look, find the quotient. Now, if they want us to find the quotient, then we have to literally use either long division or synthetic division and the remainder. So let's do that first. So for this one, we're not using the remainder theorem, right? We're just basically finding the quotient, which if I'm going to use synthetic division, so that means I would put a -2 here. What would this be? It'll be 8, -2, 10, 1, -21. So 8, then let's perform the process. -2 times 8 is -16, which is -18. -18 times -2 is 36. 46. 46 times -2 is -92, which is -91. -91 times -2 is 182. Minus 20 is 162. 162 times -2 is -324, which is -323. Okay, so what's my quotient? The quotient is going to be 8x to the 4th minus 18x cubed plus 46x squared minus 91x plus 162. And then my remainder is going to be plus -323 over x plus 2. And there's my remainder. Okay? Now, for part B, we're being asked to use remainder theorem to find p of -2. So in other words, we're saying, okay, find the remainder of this guy now. If you try to divide it by x plus 2, which if you try to divide it by x plus 2, the remainder theorem says, well, if you plug in -2 in for x, so p of -2, you should get your remainder. And we better get -323. If we don't, then there's a mistake somewhere here. So what is this? 8 times -2 to the power of 5 minus 2 times -2 to the power of 4 plus 10 times -2 cubed plus -2 squared minus 20 times -2 plus 1. And I'm going to use a calculator here just real quick to see what happens here. So if I take -2 to the power of 5 times 8 is, this is -256. This becomes what? 16 times -32, or times -2 is -32. That becomes -80. That becomes 4. That becomes 40. That becomes 1. So what do we get here? And sure enough, all this adds up to -323, which is saying, hey, if you divide this polynomial by x plus 2, you will have a remainder of -323, which, notice I was saying the same thing as that, which means we can't cleanly factor out an x plus 2, right? So that's kind of getting us into the next concept, which is basically the factor theorem. And the factor theorem says the following: if C is a 0 of P of x, right, which means if it's a 0, it's an x-intercept, then x minus C is a factor of p of x. So in other words, we're basically saying, look, if c is a 0, then x minus c is a factor of p of x, which means x minus c could be factored out. And better yet, think of it this way. We could even use the remainder theorem. If I plug in c in for x, my output, what should my output be? It should be 0, which means my remainder is going to be 0 if I try to divide by x minus c, which means that I can cleanly factor out x minus c without having a remainder. And that's what we care mainly about. So let's look at example 4 and 5, and then that'll wrap up this, the notes to this section. Let p of x equal to x cubed plus 21x squared minus 157x plus 135. We could say, look, use the remainder theorem to decide if p of 1 is a factor of p of x. And then we're going to say if it is, write it in factored form. So basically we're saying, hey, look, if it is, then factor it. So let's first check. What's p of 1? It'll be 1 cubed plus 21 times 1 squared minus 157 times 1 plus 135. Right? I just literally plug in 1. And what do we get here? We get 1 plus 21 is 22. Negative 157 plus 135 is negative 22. And sure enough, it zeroes out. So what does that mean? The answer is yes, it is a factor, because my remainder theorem is saying this is going to equal, this is a 0, right? So then to factor out an x minus 1, so what is this basically saying? X minus 1 is a factor, right? So to do this, I'm going to use synthetic division. So if I put a 1 here, then I have 121, negative 157, 135. And let's see what happens here. 1, 1, 22, 22, negative 135, negative 135, 0. So look at what we just did. We factored out an x minus 1, and if I factor it out, it'll become x minus 1 times, and what's the new polynomial I get when I factor out an x minus 1? It's this guy right here. And remember, the degree is 1 less. So if this was an x cubed, now I factor out an x minus 1, so this is going to be just a 1x squared plus 22x minus 135. So notice how I was able to factor it out with a remainder of 0, obviously, because that's what we like. Okay, now for example 5, we're going to work backwards. Find a polynomial of degree 4 that has zeros of 1, 3, and 4. Okay, so if I want to find the polynomial, well, let's go one step at a time. And my polynomial has to be of degree 4. So here's what I know. Since we have a 0 of 1, what does that mean? X minus 1 is a factor. Okay, and then if 3 is a 0, then x minus 3 is a factor. All right, I'm just using my factor theorem. If 4 is a 0, then x minus 4 is a factor. Now, if I want a polynomial that has all 3 of these zeros in it, then my polynomial function has to have what? X minus 1 as a factor, x minus 3 as a factor, and x minus 4 as a factor. It has to. So I have to multiply these together, and if I multiply them, I won't lose the fact that 1, 3, and 4 are zeros. Now, here comes the next part. What's the problem with this? If I multiply this out, I get a polynomial function of what degree? I get a polynomial of degree 3, because x times x times x is x cubed, but we need degree 4. So what does that mean? Since these are my only zeros, what I could do is, you can either add an extra 0 if you want, like you could say, I need to have another x here. So you could put an extra x here if you want. Now, this is where it's up to you. But I could say, for example, well, I have multiple zeros, or a multiplicity of 2 at x equals 1. So now notice, by me squaring this, what do I get here? I get x squared, x cubed, x to the 4th. Now the square you could have given it to the x minus 3, x minus 4, and so on, because we had to make sure that this was of degree 4. Okay, so this basically satisfies the question. And remember, there's more than one possible solution here, but this one is good enough, so I'm going to take that and go with it. So this wraps up the notes to section 3. If you have any questions at any point, don't hesitate to ask or even email me with your questions.